In this module on digital logic, we will talk about canonical forms of Boolean function representation. Having represented in the canonical form, we will also see how do we implement using logic gates. These are typically implementations which will result in two-level implementation. There are two different forms possible. We will see both with examples. Digital circuits can broadly be classified into two categories. One is called combinational logic circuits. Here the outputs of the circuits depend only on the present values of the input. The second category is called the sequential logic circuit. Here the outputs of the logic circuits depend not only on the present values of the inputs, but also on the previous values. Now, Boolean algebra is used for describing the properties of the digital systems, used for both combinational and sequential logic. Digital logic circuits can be represented with the help of Boolean expressions which relate the output of the logic circuit with various inputs. There are different ways of writing the Boolean expressions. We will talk about two forms of representations. These are called the canonical forms of representations, where the output of a digital circuit is represented as a function of the inputs. One of the form is what is called the sum of the min terms form. Here the circuits can be implemented using two-level implementation. That means, if the circuit is represented in what is called the sum of min terms form, then that circuit can be realized using two levels of logic circuit. The first level is set of AND gates followed by an OR gate. So, we call this kind of an implementation as an AND OR implementation, which is a two level implementation. First level is an AND section, second level will be an OR section. The combinational or sequential circuit can also be represented in another form, what is called the product of max terms form. So, when we represent the digital circuit in product of max terms form, again the circuits can be implemented in two levels. First level will be an OR function, second level will be an AND function. So, we call this implementation as an OR AND implementation. That means, both these canonical forms of representations which are representing the digital circuits, one is called the sum of the min terms form, other one is called the product of the max terms form. These are representations which are helpful in describing digital circuits using gates. Both results in two level implementation. One results in an AND OR implementation and the other results in an OR AND implementation. So, we will try to understand both these forms with examples. So, we mentioned about sum of min terms form and product of max terms form. So, what is a min term or what is a max term? So, let us see an example. So, here I have a function with three inputs are x, y and z, and various combinations of the inputs are listed in this table. Now, these inputs assume, because of three inputs, 8 different combinations, all inputs 0 up to all inputs 1. Now, when we talk about a min term is a term consisting of all the literals. When I say literals, which are the inputs of a given function. So, a term consisting of all the literals either in the true form or in the complement form. That means, min term is a term. Now, a term what I refer to a product term. So, min term is a product term consisting of all the literals of a given function represented either in the true form or in the complement form. So, for a 3 variable function with variables as x, y, z, the possible min terms are listed here. For example, if my x is a 0, y is a 0, z is a 0, we represent this as x bar, y bar, z bar. If x is a 0, y is a 0 and z is a 1, we represent this as x bar, y bar, z. For example, if x, y, z all are 1, we represent it as x dot y dot z. So, what we got here is 8 different terms, each one representing one set of input combination and represented as a product term made as a function of the input variables. In this table, we also indicated another column called a symbol or designation of these terms. It is only a symbolic representation of the min term. Min term, so we use a letter small m, and the suffix 0 indicates in this example binary 00's equivalent in decimal value. So, 000 in binary results in a decimal 0. So, that we indicate here as 0, that means x bar, y bar, z bar correspond to min term m0. X bar, y bar, z, which means 001, decimal equivalent is 1. So, we call that min term as m1. So, like this we can write all these min terms by an equivalent representation. For example, x, y, z, when all of them are 1, that min term is called m7. Therefore, min term is a product term consisting of all the literals of a given function represented either in the true form or in the complement form. Then let us look at a max term. Like a min term, max term is a term consisting of all the literals of a given function either in the true form or in the complement form, but the difference is min term is a product term, max term is a sum term. For example, I have a max term x plus y plus z corresponding to inputs x equal to 0, y equal to 0 and z equal to 0. That means, if my input literals x, y, z all have a value 0, the corresponding max term is x plus y plus z. Min term is represented by a small m and max term is represented by a capital M. Since x equal to 0, y equal to 0, z equal to 0 corresponding to a decimal equivalent of 0, we call this as m0. Capital M0 is a max term corresponding to the inputs x, y, z 0, 0, 0. Now, input x0, y0, z1 results in a max term x plus y plus z bar represented as m1. So, what you notice here is in the max term, when you write the input literal, you write the true value of the literal if the input signal corresponding to that literal is 0. You write the complement value of the literal if the input signal corresponding to that literal is 1. For example, x is a 0, y is a 0. So, we represented x plus y. Since z is a 1, we represented it as z bar. So, we could write for all the other terms. For example, if you take x equal to 1, y equal to 1, z equal to 1, what we get here is x bar, y bar, z bar, x bar plus y bar plus z bar, max term m7. That means, min terms and max terms are the product terms and sum terms of a given function, in which the term consists of all the literals of a given function represented either in the true form or in the complement form. Having discussed min terms and max terms, let us see what is the sum of min terms expression. As it is mentioned here, sum of min terms expression is a Boolean function representation of a digital circuit. The circuit is represented as a sum of min terms expression, in which if we plot the function of the digital circuit in a truth table with inputs and outputs represented in the table, we could look at the output column and see where the outputs are 1. Pick those min terms where the outputs are 1 and write sum of those min terms. The sum represents here an R function. So, write sum of those min terms as an expression for the given circuit. So, let us look at an example. This is an example where a digital circuit having inputs x, y, z, two outputs f1, f2, functionality plotted in the form of a truth table. A truth table is a table which relates inputs and the corresponding output for a given circuit. For various combinations of the inputs x, y, z, the corresponding output values f1 and f2 are plotted in this table. For example, if you take the output f1, various output values of F1 for the given set of inputs are plotted here. Same thing is for F2 also. So, for example, if you look at the output column corresponding to F1 and try to pick those entries where the outputs are 1. Output is a 1 here, for which the inputs are x0, y0, z1. The minterm corresponding to that is x bar, y bar, z. For another output value F1 1 corresponding to x0, y1, z0. So, we will write that as x bar, y, z bar. Then we have a third entry where x is a 0, y is 1, z is 1. We call this as x bar y z. And the last entry is x is a 1, y is a 1, z is a 0, x dot y dot z bar. When we write the function f1, it is sum of all these minterms, which is an OR function. So, I am going to put an OR operator between these minterms. So, what I get here is the function f1 is x bar y bar z plus x bar y z bar plus x bar y z plus x y z bar. We call this as sum of minterms expression for the given circuit whose outputs f1 is represented like this. We could do the same thing for f2 also, picking the entries corresponding to f2 equal to 1, and we could write the expression in the form of sum of minterms for f2. We talked about sum of minterms expression. Sum of minterms expression is useful in realizing digital circuits in a 2-level implementation. So, the example what we talked about in the previous slide gave an expression for f1 as x bar y bar z plus x bar y z bar plus x bar y z plus x y z bar. Each one of them is a product term. To realize a product term, which is a minterm, we require AND gate. So, we require 4 AND gates, each one generates a product term. So, we get 4 product terms, which are also called minterms. The outputs of these AND array is connected to an OR gate, and the final output f1 is what we realize here. So, we call the first set of AND gates represents level 1 and the OR gate represents level 2. We call this as 2-level implementation. The meaning of 2-level here is, if you apply inputs either in the true form or in the complement form, these inputs have to pass through a set of gates. It takes some delay, depends on the propagation delay of these gates. If I assume all these gates are having equal delay and call the delay as n1, we get the intermediate outputs after time delay n1, which will now then pass through the second level, which is an OR gate, and if we assume the delay of the OR gate is n2, the total time it takes to get the final output having applied the inputs is n1 plus n2. So, we call this implementation as a 2-level implementation. Each level adds the delay to the logic circuits function, but first level having all AND gates, second level having OR gate, we call this as an AND OR implementation. This AND OR implementation can also be converted into what is called a NAND realization. For example, if I insert a bubble here as well as a bubble here, which means I am NOTing the function as well as NOTing the function, NOT of a NOT, there is no change in the function. So, if I keep doing that, inverting the outputs and the inputs for all these cases. So, now I get the first set of gates as NAND gates. This is an equivalent representation of a 4 input NAND gate. So, I also get the second level as a NAND gate. That means the same circuit is now realized in 2 levels using 2 levels of NAND gates. It is called a NAND realization. That means the sum of a minterms expressions can be realized in 2 levels using an AND OR implementation or an AND NAND implementation. Let us look at the second form of representation, what is called the product of max terms expression representation. Digital logic circuits functionality can be represented using a product of max terms also. As it is given here, a product of max term results in max terms which are nothing but sum terms. We should pick those sum terms in a given function where the output value corresponding to the set of inputs is 0, and then find the product of those max terms. Product refers here an AND function to realize the function in product of max terms expression. So, let us take the same example. The inputs are x, y, z, outputs f1, f2. What we do now is look at the output column and pick the outputs where the value is a 0. For example, my f1 is a 0 here corresponding to x 0, y 0 and z 0. The corresponding max term is x plus y plus z. Output f1 is 0 corresponding to x1, y0, z0. The corresponding max term is x bar plus y plus z. Then we have x1, y0, z1, x bar plus y plus z bar. Finally, x, y, z all 1 corresponding to x bar plus y bar plus z bar. There are 4 max terms. If you want to write the function f1, this will be AND function of these max term. We will put a dot here and a dot here, which means x plus y plus z and x bar plus y plus z and x bar plus y plus z bar and x bar plus y bar plus z bar. That means the given function can be represented in the product of max terms. Max terms are those terms which are made as a function of all the input literals, and it is a sum term, and product of those max terms will result the given digital circuits representation as a 2-level representation. We could now draw the circuit implementation for this product of max terms implementation. We will have the first level as set of OR gates, because each one is a sum term. For this example, we had 4 sum terms, so we require 4 OR gates. The terms were x plus y plus z, x bar plus y plus z, x bar plus y plus z bar, x bar plus y bar plus z bar, which now pass through an AND gate to get the final output of f1 in the product of max term form. The first level is set of OR gates, second level is AND gate. We call this as an OR AND implementation. Now, like the previous example, I could put bubbles in these entries, invert the output of the OR gate as well as inverted the input of the AND gate. Now, this becomes an equivalent representation of a 4 input NOR gate. So, what I get here is circuit implemented using 2 levels of NOR gates. So, we also call this as a NOR implementation. So, let us take an example of a combinational circuit design. The circuit's functionality given here is a combinational circuit which is called a majority circuit. In this example, the circuit has 3 inputs and an output. It is a majority circuit, which means the output is equal to logic 1 if input variables have more 1s than 0s. Draw the truth table, write down sum of min terms expression, realize using 2 levels of NAND gates. So, let us try to plot the truth table for a given function. It is a 3 variable function. So, all the input combinations are listed in this table. As per the problem statement, output is a 1 when majority of inputs are a 1. So, my output is going to be a 1 here, output is going to be a 1 here, output is going to be a 1 here, and output is going to be a 1 here. These are the 4 cases where you have more 1s than zeros. In rest all places, outputs are zeros. The circuit's behavior is now represented as a truth table. We need to identify the min terms. We know the min terms are those terms where look at the output trend entries and corresponding to output value is equal to 1, pick the corresponding inputs. Output is a 1 here, the max term is x bar y z, ORed with x y bar z, ORed with x y z bar, and finally x y z. So, the function f in the sum of the min terms form results like this. We could convert this into a logic circuit using gates. We could do an AND OR implementation or a NAND NAND implementation. So, we will have the first level AND gates followed by the second level OR gates, which is becoming an AND OR implementation. We could also make both levels as NAND gates, that will become a NAND NAND implementation. For example, I will have 4 NAND gates here, because we need 4 min terms to be generated, whose output pass through a 4 input NAND gate, and the final output f will be the given function as per the expression given here. A combinational circuit can be realized using array of NAND gates if it is represented in sum of the product form of representation. So, in this module we talked about canonical forms of representations, that means how to represent a digital circuit in sum of the min terms forms and the product of the max terms forms. Both of them helps in realizing the digital circuit in 2 level implementation, either an AND OR implementation or an OR AND implementation.